Hello, everybody. Welcome to the SETI Institute Colloquium for today. I'm Mark Showalter. I'm a senior research scientist here at the Institute, and it's my real pleasure to introduce Jeff Moore. Jeff Moore and I have gone back decades. We were both postdocs at NASA Ames in the early 1990s, so I've known Jeff for quite a long time. Jeff is currently a research scientist in the Space Sciences Division at NASA Ames. After the postdoc, he came to the SETI Institute, and he was a research scientist here for a couple of years before he got the call of the civil service. 7 years. 7 years, Jeff says, that he was here before he got the call of the civil service and went back across the highway to NASA Ames, where he has been ever since. In an earlier life, I should just note that in the 70s, Jeff received a personal invitation from President Richard Nixon to serve in the U.S. Army, and he was a tank commander in the 1970s. So be respectful here. There are sides of Jeff we don't all know sometimes, I think. Jeff is currently also a good coworker of mine, colleague. We're working together on the New Horizons mission. Jeff is my trusted leader as the Geology and Geophysics Imaging Science lead. And of course, we have a very exciting encounter coming up in just less than 2 months. So we're very much looking forward to that. So without further ado, let me introduce you to Jeff. His talk is Geology Before Pluto, Pre-Encounter Considerations.
Thank you, Mark, for that kind invitation. So this talk is a combination of things. It's an introduction to the mission itself and to the Pluto system itself. And it's also the slide version of a paper which was full of our ruminations about what Pluto and its moon's geologies might be like, that was published in Icarus last year. So as you can see, this first slide just shows an artist's conception of what Pluto might look like. But let's kind of dive in. So Pluto is actually a member, kind of a third zone of the solar system. We have the inner solar system made up of the 4 terrestrial planets. We have the realm of the 4 gas giants and their satellites, the large satellites which travel with them. And then there's this sort of third zone of the solar system, the Kuiper belt, which may contain maybe as many as 1,000 dwarf planets. But Pluto is a good representative, if not perhaps one of the best representatives of this collection of objects. It's either the largest or amongst the largest we've discovered so far. It has one large natural satellite in addition to several smaller satellites, most of which have been discovered by Mark. And as you can see, that maybe only Eris even competes in size, at least of the objects we've seen so far. The best HST images of Pluto show that it has very strong surface variation. It has amongst the brightest and darkest surfaces of objects we see in the solar system. It has locations on the surface where as bright as new-fallen snow and other places which appear to be as dark as asphalt. It's very colorful. It has some of the reddest stuff people have seen. And this is just entirely based upon observations made from either Earth-based or Hubble imaging. So we already know that there's a lot of contrast on the surface. Also, we know its surface composition is made of a number of interesting materials. We know that it has methane on the surface, discovered back in the 1970s. It has a large component of nitrogen ice and carbon monoxide ice. And the methane and carbon monoxide show weird, patchy distributions. But we do know that largely the surface is being dominated by nitrogen ice. We also know that it has an atmosphere. It was first detected back in the 1980s. The first occultation showed an extinction around 10 microbars. But that could simply be at what point the atmosphere becomes too refractory to continue to transmit the star's light through it as the occultation proceeds. And so we really don't know what the atmospheric pressure of the surface of Pluto is. It could be 50 microbars or more for all we know, or 100 microbars. That's one of the things we hope to find out with the encounter itself. We know that we expect there to be strong seasonal effects because, as I think most all of you know, that Pluto has a highly eccentric orbit. It travels many AU further from the sun during its aphelion than during its perihelion. It also has the strange effect of having its equinoxes at perihelion or aphelion. So there's all these extreme seasons operating on Pluto. So we know Pluto has extreme seasons. We know Pluto has all these volatile materials on it. We know that it has all this high contrast surface. And of course, these high contrast surfaces on these thin atmosphere planets mean that the dark surfaces warm up and the bright surfaces cool off and so on. So we have the expectation there's lots of stuff happening on Pluto. So you might say, well, based upon just the fact it's very contrasty, Pluto might be at least as interesting as Iapetus. But I'll make the argument that Iapetus doesn't have an atmosphere, or Iapetus doesn't have all these volatile materials on it, and doesn't have extreme seasons. So I think we will be pleasantly surprised when we start seeing the really good pictures in July. Also, you can't entirely judge a book by its cover. We already know from the size and masses of and modeling done of Pluto and Charon, at least, that Pluto is mostly a rocky body, not an icy body. It simply has a thick, icy mantle. And this particular model from Bill McKinnon and his former student, and Damon Simonelli, that it has a large rocky interior, it has an icy rine, and it has a very thin layer of the more volatile and lower density materials like nitrogen and methane. And interestingly, Charon, or Charon, however you want to pronounce the large natural satellite, probably has a relatively undifferentiated interior with a thin, several kilometers thick outer surface or outer crust of more pure water ice. And it's even possible, according to some of the modeling, that we will find that there is actually perhaps a little liquid water layer at the interface between the rocky core and the ice mantle. Now, as I mentioned, back in the 1970s, we discovered the first of Pluto's moons. It's one very large moon, almost half the size of Pluto itself. We see that it had a 6.4-day period, and since Pluto and its large satellite face each other, that means it also has a 6.4-day-long day. Charon's surface is interesting. It seems to be almost entirely dominated by water ice, and apparently there's no detected atmosphere. Now, thanks to work initially by the people at APL, but more recently by Mark almost solely, Mark Showalter, who, as you know, just did the introduction, we have discovered there's a collection of smaller satellites. Nixon Hydro discovered early. They were discovered early enough that, in fact, when we were planning the encounter, we were going to actually take some pretty good pictures of those satellites. And then we discovered these other new satellites that Mark's responsible for, Hydra and Kerberos, which we will see probably disk resolved. That's to say, they'll be greater than a few pixels across. But because of the lateness in which they were discovered, we really couldn't add them into the encounter. And part of the problem, as you'll see in a subsequent slide, is because they sort of fly up on the system all at once, like flying into a bullseye. You have very little time to do kind of all your work. So for that reason, some sacrifices had to be made. The satellite origin, well, most people think that something not too dissimilar from the explanations offered for the formation of the Earth's moon also played a role in the formation of Charon and its smaller satellites. The dynamics of the system, including its smaller moons, is consistent with this idea of a large impact in the Kuiper belt region relatively early in solar system history, creating all the moons that we see there today, including Charon. Let's change subject now to the spacecraft itself. So we launched in January of 2006, the time we left the Earth's orbit on our transplanetary trajectory burn. We were the fastest object ever to leave the Earth's orbit. We crossed the orbit of the Earth's moon in 9 hours, in contrast to the 3.5 days it took the Apollo astronauts to get to the same location. We did a flyby of the Jupiter system about 13 months later, from which we were able to steal some of Jupiter's orbital momentum and increase or decrease our travel time by another 2 years, allowing us to arrive, as you now know, in July of this year at the Pluto system. So here's our spacecraft, and since I'm a geologist and and certainly not a fuels and particles person. I'm going to kind of not talk about what these two fuels and particles instruments do, except you may hear me allude briefly to escaping atmospheres and things like that, and that's the sort of thing these instruments measure. The things I'm mostly interested in are the high resolution narrow angle pictures, which are grayscale images, will be taken by the LORRI camera, and then this instrument, Ralph, is a 2-component camera. It has a near IR imaging spectrometer detector head, and it has a higher resolution wide angle visible color camera detector head called IMVIC. So, and I'll show you some images of what the footprints from these two cameras look like here shortly. But the principal thing to remember is the LORRI is a framing camera. It takes a 1024 by 1024 pixel image. It's a grayscale. And IMVIC, which is part of Ralph, which will take a much wider field image. It's 4 times coarser in linear pixel resolution, but it also takes color pictures. So you can imagine we'll do all kinds of things like colorize our high resolution black and white images and things like that with the color data we take from that camera. Now here's our closest approach geometry, and this goes to emphasize the point I made earlier about this being something like flying into a bullseye. As a geologist, I have to say that probably most of the data that will be collected, that geological analysis will be performed on, will probably be collected within a 24-hour period around closest approach. So for me, after being involved in this mission for 15 years, gravy day is literally a day. I mean, we will, because we have the long-range narrow-angle telephoto camera, we will see the opposite hemisphere of Pluto 3 days before, and it will still be imaged at around 15 kilometers per pixel. So all the visible surface that currently has sunlight falling on it at least will be seen at least at 15 kilometers per pixel. But the near-encounter hemisphere, well, as I'll show you some examples of what that encounter will look like, and I think you'll see that that's where I hope a lot of interesting geological observations will be made. Okay, here are some of the encounter highlights. This is from one of Alan Stern's slides. There's approximately 7 months of encounter science at Pluto. We will exceed Hubble resolution for about 3 months. I think we're just now kind of moving into the beginning of this period. We will map the entire sunlit areas of Pluto and Charon. We'll make global composition maps of Pluto and Charon with the near-IR mapping spectrometer I mentioned called LISA. We actually have a passive radio mode to our radio antenna, which we use to do thermal mapping. So we'll map the temperatures of Pluto and Charon on both the daytime and the nighttime sides. We will directly measure Pluto's atmosphere and its escape rate, its pressure, temperature, composition, the whole 9 yards. We'll do a very thorough bang-up job on that. Part of that reason is because we're passing in the shadows, both the sun shadows and the radio shadows as seen from the Earth of Pluto and Charon. And we have a sophisticated radio science experiment, which is actually largely designed and managed by people at Stanford, to very precisely measure information from the occultations that will give us the information about the structure and pressure, et cetera, of these atmospheres, composition, so on. We will improve the interior structure models and get a better sense of how well differentiated Pluto and Charon are. We'll obtain high-resolution images of Nix and Hydra. We'll make compositional measurements of Nix and Hydra and some of the other smaller moons. And we'll see if we can identify any additional Pluto system satellites. And we will be searching for rings, which again goes back to stuff that Mark is doing. And Mark probably either has talked to you about this or will talk to you about this. Okay, so that's on to the paper. Now I should have updated my slide. It's no longer in press, it's out. So if anybody, by the way, is interested in this paper, by all means, just send me an email. I'll be happy to send you a PDF. So let's talk a little bit about the encounter itself. Here's an example of some of these narrow angle framing images, footprints of them being laid down on Pluto at about 90 minutes before closest approach. Now I'm showing you this image because we're going to cover the very same area again right at closest approach with the wide angle color camera. And in both cases, because of this, the spacecraft will be much closer to Pluto at this point, because you see the size of these footprints here. Well, this is the same camera and the same footprints, now much smaller on the disk because we're much closer to Pluto. But the point of this is we will cover both this major near encounter hemisphere with the two cameras at nearly the same resolutions, but at different viewing geometries. And by doing that, we'll be able to generate a near global topographic map of at least of the encounter hemisphere, which will have resolutions of around 120 meter vertical resolution and about a 1 kilometer horizontal resolution. And that will be our best stereo coverage. Not to mention the fact this little strip of images will nominally image the surface of Pluto at about 70 meters across. We'll also take a second set of stereo images that are a little coarser resolution. This is the last mosaic we make, which captures all of Pluto. And then in between the two images I showed, the two observations I showed you in the previous slide, we'll do a scan again with MVIC, which will produce the complementary stereo pair, from which again will produce some very high quality stereo information. So anything that is basically visible on the surface of Pluto on the day of the encounter, we will have good to very good topographic information on the surface. And topographic information is essential in being able to understand what geological processes operate on a surface. A lot of things in map view may look similar, but could be formed by other processes. And the best way to differentiate between which process actually forms something is to have real knowledge of the slopes of the objects and the total elevation of the objects. And so this will be a very important diagnostic tool for us in interpreting what are the processes which have operated on the surface of Pluto and Charon. We'll also get good pictures of Charon. Here's an example of one of those lorry frames I mentioned earlier. And you can see we'll get imaging that ranges down to 150 meters per pixel on the surface of Charon itself. Now here's some examples just to show you from using other worlds of what kinds of resolutions we'll be getting. So the entire near encounter hemisphere will have global coverage at around 300 meters per pixel. Here's a view of Jupiter's moon Europa at about that same resolution. So I think you can see that we'll be able to recognize a lot of interesting textures and details. And this is also about the similar lighting, the sort of lighting we'll have during near closest approach with this kind of resolution imaging. Here is an example of what's actually a MOLA DEM for Mars, but this MOLA DEM has been sampled with contour lines and horizontal and vertical resolution to basically be equivalent to the quality of the topographic information we'll be able to derive from our stereo images. Here is a sense of our highest resolution images with around 70 meters per pixel. This happens to be Iapetus. This also emphasizes the importance of making sure you have good stereo data, because we anticipate that because Pluto has these volatiles on the surface, where you could imagine that the slope facing towards the sun is losing ice and getting dark, and the slopes away from the sun are getting cold and collecting frost, that you could actually have contrast reversals on the surface. And if you simply looked at an image and tried to derive shape from shading, you could be deceived. But if we have the actual topographic information, we really do know what's up and what's down. It's very important in getting our story together. We'll, of course, collect all sorts of crater statistics and crater morphologies. So we can both learn from the crater morphologies as crater shapes change with increasing diameter, what that's telling us about the interior of Pluto and Charon. We've learned from looking at other icy worlds that very often, particularly icy worlds that have had or still have warm interiors, the shapes of the craters change radically as they get larger. And then, of course, we're also interested in the crater statistics, which will allow us to get a much better sense of two things. What is the crater flux rate in the Kuiper belt, which is something we don't know, and also allow us to make some determination about at least relative age, and not absolute age, of the various surfaces we see in the Pluto system. We'll also look at the matters of sedimentation and erosion, which are markers of volatile transport. There are some interesting non-reversible processes such as scarp retreat, which is called decrescence. It's a formerly larger surface. As the scarps retreat away, have pointed protrusions and scalloped retreating surfaces. And then at some later time, the process reverts itself, and this now scallopy looking surface begins to accumulate material again along its side. It reverses the process where what was a point now becomes a blunted protrusion, and so on. So by looking at what kinds of shapes you get between these two, we can recognize whether we're seeing multiple episodes of decrescence and accrescence, or is everything just accrescing or decrescing. It's perfectly possible that given the atmospheric escape rates for Pluto, that over the lifetime of Pluto's system, it may have lost a couple of kilometers of ices. So we may see a surface that's largely decrescent, at least on a regional or large scale. And here down at the bottom, you can see some examples of decrescence, and particularly this is an interesting picture because this is what's often held up as a possible twin, maybe fraternal twin to Pluto Triton, Neptune's moon Triton, in which you see this sort of decrescent surface operating. It has much the same kinds of volatiles that Pluto has. And also you can see there are some of these little plumes, which are probably, we think, solar powered from the so-called solid state greenhouse effects. And so we'll, of course, be looking for things like that. If you see plumes, that will be interesting and aesthetically attractive, and tell us a lot about the winds, and also tell us a lot about the uppermost surface of Pluto. Of course, we're also interested in just more traditional mass movements. Here's a very long landslide, a 50-kilometer long landslide on Iapetus. There's also these weird long-distance mass movements you can see, like on one of Saturn's small moons, Helena. It's perfectly possible. This is about the same size as the smaller moons of Pluto, so we'll be looking at the surfaces of the small moons of Pluto, like Nix and Hydra, to see if they have these sorts of processes. This may be due to the slow accumulation of material onto the surface of, in this case, Helena, and we can imagine similar circumstances where there might be the slow accumulation of material onto these small moons as well. And as I mentioned earlier, there is a lot of volatiles, a lot of probable volatile movement on Pluto at least. And so we'll be looking for evidence of sublimation degradation. And here you can see an example of this process where you start with an initially unsegregated, undifferentiated surface, which has a combination of refractory material like dirt and volatile material like various types of ices. And as the surface is heated up, what happens is you get local cold traps where summits see less of the surrounding warm terrain. And then likewise, you have depressions, which see a lot of the re-radiated heat from the nearby slopes. And with time, what happens is these spots become points in which frost collects, whereas the depressions, which see a lot of their local slopes, nearby slopes, become net collectors of dust and material. And here's an example of that process operating on Callisto. We're also very interested in whether we'll see maybe Aeolian activity on Pluto. Calculations have shown that if some of the higher values people have predicted might be applicable to at least some episodes or some periods in Pluto's either its seasons or in its history, reaching these higher values of 50 microbars or better, that in combination with modeled winds could produce incipient dune formation or ripple formation. The calculations for these features suggest they may be at the limit of resolution, so we'll be curious to see if we can pick these out and if they're there, or do we see other markers on the ground that suggest that we're seeing Aeolian or wind-driven processes on the surface. Of course, we're interested in endogenic processes. In this case, tectonics is the first case. It'd be a little surprising if there isn't some expression of tectonics on both the larger objects, Pluto and Charon, and certainly one would expect to see it on Charon. I put Ariel in this slide only because Ariel is the same size as Charon. It has the same density as Charon. So just because something is the size and density of Charon doesn't mean cool stuff isn't happening. So we'll stay tuned to see what kinds of interesting in this case, mostly tectonics and perhaps some so-called cryovolcanic features have operated on the surface of Ariel, maybe be operating on the surface of Charon and perhaps Pluto. And here are examples of similar types of tectonically shaped ridge systems. In this case, there are different scales, as you can see, and here they are operating on Jupiter's moon Europa. Here are examples of them operating on Neptune's moon Triton. Also, it's perfectly possible because we do have these very low volatile materials, and because much of the interior of Pluto is made of rock, there could be enough radiogenic material in the rocky interior of Pluto to gently warm this very volatile material, and we could have so-called cryovolcanism or low melting point ice volcanism operating on the surface. And so we will look for and see, and we'll try to determine if we see any volcanic features. Here's probably the best, the least controversial example of an icy volcanic feature on Triton. This is Leviathan Patera, which bears a lot of resemblance to things like the sorts of large volcanic centers you see in New Mexico and Wyoming. Here is a smaller caldera made mostly largely in a water ice crust that's formed on Ganymede. But there's a cautionary tale to all this because we thought, based upon lower resolution images we took in the early 1980s from Voyager, that this surface on Enceladus was entirely volcanic because it seemed to be smooth, it seemed to be embaying pre-existing topography. But when we saw it at much higher resolution by Cassini, we discovered, in fact, it's entirely tectonized, and if there's any volcanic resurfacing involved in the creation of the surface, it's not obvious. So we need to be careful and not jump the gun and proclaim that we've discovered cryovolcanism when it may actually be some other process. Now, of course, the irony to this is that Enceladus does have, a form of icy volcanism. It may, in fact, have the best example of icy volcanism on it because it has these vast plumes erupting out of its south polar region, which I think you've heard people talk about here before. So one of the principal tools we will use to try to understand the interplay of geological processes which operate on Pluto and Charon is landform evolution modeling. This permits us to do an interplay of various geological processes. We can turn them off in sequence. We can run them at different rates. We can have them come and go. And we can do that to try to mimic closely as possible the final product surface we see. And the mechanism we often use to try to understand whether our modeling is converging on a realistic answer is that, again, because we're collecting real 3D statistics, topographic statistics, we can run a series of different parameters and the different types of geological processes which might play and see which combination of those geological parameters in the model produces a statistical landscape or a model landscape with statistics which most closely match the statistics from the real landscape. And so by doing so, you will have a much better understanding of which geological processes operated and when and how intense they were. And of course, all this, particularly these sedimentary processes, the exogenic processes like erosion, transportation, deposition, will have implications for the, quote, climate of the past and present of Pluto in particular. Okay, so at this point, I will say we're on our way. We'll be there in less than 2 months, and we'll be arriving on Bastille Day, and the French didn't pay us anything extra for that to happen. And so with that, I end my talk, and I'll take questions.
Yep. Thanks, Jeff. Let's thank our speaker. Okay. Questions? Wait for me to bring the mic to you, please.
I will make one quick comment, which I hope I can give you a much more interesting talk next spring.
So is there going to be a website where the control station that's processing all this is that we can access during this time?
Yes, the Applied Physics Laboratory of the Johns Hopkins University, simply known as APL, has a public site which will post particularly the LORI images, which are the high resolution framing images on our site within, I think, around 24 hours after they are first acquired. It's very similar to the setup that JPL has for images that are collected by the Cassini spacecraft.
That's actually online right now. You can get star fields with a oversaturated Pluto and Charon in it. They're the ones we're looking for small moons right now, in fact, but they're online.
So what targets in the Kuiper belt is the spacecraft going to look at, and how long will it take for it to get to its next encounter?
Well, fortunately, we were able to get some Hubble time last year, and we found a couple of Kuiper belt targets which we can reach. Now, we still have to we have to write a proposal to NASA and get funding to actually operate the spacecraft when we get there, but we would be arriving in the vicinity of whichever target we ultimately select in early 2019. So write your Congress people, tell them if you want to see one more Kuiper belt object, that we need the resources to do it.
Over here.
Oh,
Hi.
hi.
What kind of resolution are you going to get on the smaller moons, and will you be able to track their orbits enough to infer something about their composition based on the gravitational pull they have on each other?
You should ask that to Mark more than myself. I can answer the question about the resolution that we'll get several 100 meter per pixel imaging of one of the smaller satellites, and we'll probably get around 1 kilometer per pixel on one or two more, and then after that, not so much.
Yeah, the masses come from long-term tracking. The flyby is too fast to actually get much information about the masses in particular, but that will come over time. Questions?
What would be powering the geologic processes? Is there some heat generating mechanism? I mean, some cases are tidal.
Basically, there's two. One is the sun. That's what drives sublimation, precipitation, potentially thus erosion, transportation, and so on. And the winds, if there are wind-driven processes operating, those are all basically solar-powered. And particularly since Pluto is much closer to the sun during its perihelion than its aphelion, that there's going to be extreme heating and cooling contrast in combination. In fact, it also has a tremendous axial tilt, where, as I say, its equinoxes occur, interestingly, at aphelion and perihelion. And then the other one be, as I said earlier, the interior is mostly made of rock. And of course, we anticipate there's the usual amount of radiogenic material heating that comes from this rock. And inasmuch as it is ultimately transmitting its heat to very volatile, rich upper crust, a few kilometers thick of nitrogen and methane and carbon monoxide, it's not unimaginable that those materials are being mobilized and will result in so-called endogenic landforms like mountains and canyons and maybe even volcanoes. Oh, sorry.
Are the photos sent immediately, or are they stored and sent in batches? And what's the time delay in between being sent and being received?
Okay, well, there's two ways to answer that question. There's an actual one-way speed of light lifetime, which is on order of around 5 hours or so to get from Pluto to the Earth. But because we wanted to make the spacecraft lightweight and relatively inexpensive, so we could get NASA to provide us the funds to build it in the first place, we use a relatively small radio antenna. So the vast majority of the data sets are stored on the spacecraft after the encounter, and won't see much of the data until months after the encounter. We're going to send back a handful of images in July. Most of them will be lossy compressed, so there'll be compression artifacts, particularly dark terrains will block up into compression artifacts. So you'll probably see me standing in front of a similar audience hemming and hawing about whether we've seen cryovolcanism yet or not, because that could just be compression artifacts. But the places which look most interesting to us, we can then plan within the first few days after closest approach to have those images sent back, a handful of them, in September, and we'll talk about what those images tell us then in the fall. And then there's the major playback, which will take place in November and December and January and February. And so as I said, if you asked me to come back again next March or April, I could probably give you a pretty good show.
Okay, will you be able to get a better idea of how differentiated Charon is between ice and rock?
Yes, but we'll have to infer that mostly based upon the landforms we see on its surface. We won't actually really make any direct gravity measurements. We're simply passing too quickly, and moreover, we're passing much closer to Pluto than we are Charon. Charon's basically over the shoulder of Pluto as we do the closest approach, which is to our advantage because since the spacecraft doesn't have a scan platform, all the instruments are just bolted on the spacecraft. You have to actually use attitude control jets to point the cameras. It takes a lot less time to point at Pluto than point at Charon and point at Pluto and point at Charon than spin back and forth to try to do all this stuff. So for a variety of reasons, we're going to see Charon, and we'll also pass ultimately behind Charon as seen from the sun and the Earth, so we'll get occultation information, but we won't actually gravitationally feel Charon in any meaningful sense.
Hi, Jeff. I was wondering, is there any opportunity to change what your plans are in flight, or is it all pre-scripted and the fly?
Oh, it's massively
pass-through?
pre-scripted, and it's been rehearsed on the spacecraft several times. There are a handful of observations which we have blank spaces where you can still say, I want to look at that instead of that, while you're still a few days away from Pluto in case you discover a new moon or a ring or something. So we can do a little bit of, there's a couple of generic spots in the schedule. We can say, oh, we already have we can set where you point the spacecraft and the exposure speed, and that's about it.
Hey, Jeff, this is kind of an interesting scientific problem since the requirements for the design of your instruments were frozen 13 years ago. Life goes on, science learns new things. Is there some instrument package that, in hindsight, you would have rather put on this spacecraft in exchange for something that's already there?
Oh, not so much, and part of the reason for that is that, yes, of course, life does go on, and there are fancier, schmancier new instruments. But there's also the real issue of making sure you're flying a highly reliable instrument that you know is going to work, because if something goes wrong, we're up the creek. So we picked instruments and components which have the highest record of reliability at the time the spacecraft was built. And I think, ironically, there aren't a whole lot of other newer instruments that have a higher degree of reliability than the instruments we're flying now. For one thing, in contrast, the cameras, for instance, the whole science package is far more sophisticated than the Voyager packages that were used. So when we can compare apples and oranges, compare Triton with Pluto. If we had flown Voyager 2 to Pluto in 1989, we'd have gotten an encounter which would be on order of magnitude coarser and less informative than the encounter we're going to get from New Horizons.
Yeah, are the cameras fast enough so you don't have to slew the spacecraft when you get really close?
The cameras are fast enough that you can actually take images while the spacecraft is moving. We have two modes. We can actually, point and stare and take a picture, and we do that, in fact, to take that series of 15 images that make up one of the two mosaics you saw me present. But also during closest approach, when you just see us do a string of images across the disk of Pluto, those are being taken as the spacecraft is moving, so we just simply shutter them fast enough that you have less than a half pixel smear. I mean, we knew where we were going, and we knew what the sunlight was like, so we built instruments which, that could collect enough photons to do the job.
It's been thought that Triton is similar to Pluto, but I don't know if that's still a principle that holds, and I don't know if recent observations on Ceres has been helpful in giving you any analogies so far.
Well, Triton and Pluto are about the same diameter, and they're about the same density, and they're both Kuiper belt objects. Triton, of course, had a very different history, and it was captured by Neptune. It was probably initially in a very eccentric orbit, and as it was circularized, it underwent tremendous tidal heating. So what the imprint of the tidal heating was on the surface of Triton, we can only imagine as being enormous, but it's difficult to imagine what its pre-tidal heated surface might have been like. So in some sense, it would be interesting to see Pluto, because we can imagine that maybe the pre-captured Triton might have had a surface like Pluto's.
Anyone else? Well, Jeff, in appreciation for your talk here, we have this commemorative mug, SETI.org/talks, which is a chance for you to show off to your friends and colleagues where you've been.
Absolutely. All right. Thank you.
Yes.
Thank you all very
Thank our
much.
speaker once again.